Welcome back to Multigrid Methods. Today I'm going to remind you of the definition of the gradient descent method for our convex optimization problem. I'll walk you, we'll state a convergence result, and then I'll walk you through the proof. And then we're going to use that as a springboard to go into chapter 12, where we're going to develop much more sophisticated algorithms for this convex optimization problem. Right. So the idea is we have some energy that is basically shaped like a bowl. And we're trying to get to that point in in this case, a plane, which we're going to call U, such that this is the minimum or minimizer of this energy E. The space over which we're operating is what we're calling V. This is a Hilbert space, and the values of E are real. So E is a mapping from the Hilbert space V into the real line, just as I've shown here. And we're making some assumptions about E so that it has a unique global minimum, unique global minimizer that we're seeking to find, this thing called U. So we want to set up a method to solve for this. And basically, this method is quite a bit similar to a method that we've had in the past, at least that we've examined in a previous course, called the steepest descent method. So the gradient descent method is like that. It's just that there's one missing feature, and that missing feature is that we don't, when we do a line search, we're not going to go all the way to the minimum in the line search. We stop at some point. Otherwise, it's basically just the steepest descent method. All right, so gradient descent, we're going to assume that E is strongly convex and locally Lipschitz smooth, just to make this a well-defined algorithm. The gradient descent method is then an algorithm for generating a sequence of points, uk from k equals 0 to infinity. So you need to start this, you need to initialize it with 1 point, u0. You fix a step size. Okay, tau is a positive number, and that's called the step size. And then you generate the next iterate from the current iterate by stepping along a certain direction, what's generally called the residual direction. And the amount that you step is going to be proportional to that step size that we choose. Okay, so the algorithm is precisely uk plus 1 is equal to uk minus tau. This is the Rees map of this linear functional. Remember, a derivative is a linear functional, and in this case, we're taking the derivative at the point uk. Looks like I'm going to have to let Ace out. Just a second. All right. For some reason, he's not happy with his current situation, so here's your toy. Okay. Sorry about that. Okay, so this is the gradient descent method. And we want to prove that if tau is chosen to be not too large, then we can always be guaranteed that this algorithm is going to converge, that this UK sequence is going to converge to our global minimizer U. So here's the statement of the theorem that we want to prove that guarantees this. Let V, of course, be our usual Hilbert space. E is our functional that is assumed to be strongly convex and locally Lipschitz smooth. We're going to assume that U is a minimizer we're going to label U to be the minimizer of E, and we know by be assumptions on E that this minimizer exists and is unique. Next, we need to pick a point, U naught, and that point can be absolutely arbitrary in V. It doesn't have to be sufficiently close. It doesn't have to have any certain nice properties. And that's because our assumptions about E are global. Our assumptions about E are absolutely global, so it's not going to matter how close we choose U naught to be, or it's not going to matter how close we choose U naught to the global minimizer U. Define B to be this set. It's a set of all V such that in distance, V is close to U, like U, or at least as close to U as U naught is close to U. So the picture is like this. We have our global minimizer, U, our starting point, U naught, and this creates a ball, right? So basically this ball B is anything in this shaded region. So it has to be all points which are as close, at least as close to U as U naught is. This is our set B. We're going to let L be our local Lipschitz smoothness constant for our functional E on this set B. And we're going to assume that our step sizes satisfy that they're greater than 0, that's always assumed, and less than or equal to, or actually less than strictly, 2 mu over L squared. Now remember we said oftentimes this constant is going to come up from time to time, L over mu. And you can see this is not exactly L over mu in this case, but it's related to it. And this is what we sometimes call the, let's see, what did I call this? The nonlinear, what did I call this? It's escaping my brain for the moment. Nonlinear condition number, that is it. Okay. All right, so if tau is assumed to be in this interval, then this sequence generated by the gradient descent method always is going to stay within B. So we're always going to be in this set B somewhere. And moreover, we're going to get a contraction. Okay, U minus UK plus 1 in the norm is less than rho times the norm of U minus UK. That means if we're close to the true solution, the minimizer, then the next one is going to be even closer by a factor of rho. So let's suppose that this distance is, say, 1, and rho is equal to half. So this is exactly half the distance, or better, actually. Where rho is, I think I discovered why Ace is so frustrated. He's got one of his toys under my desk that he can't quite reach. I'm sorry, buddy, I can't get that for you now. All right, so this rho is between 0 and 1. And so it's this long, complicated thing, which we can easily show is between 0 and 1, but take my word for it, it is. And basically it's chosen by, or it's gotten for us by assuming that tau is in this interval. What we can do later on is say, well, if tau is in this interval, maybe I can choose tau judiciously so that this rho can be as small as possible. And that's what we'll call the optimal rho. Okay, but in any case, the sequence converges at least linearly to U. This is what we mean by linear convergence, that we get this contraction at each step. Now, if there was like a square on this term, then that would be quadratic convergence, but this is what we call linear convergence. Here's the proof. So to shorten the presentation, we're going to introduce this term called the error. EK is equal to U minus UK. And we're going to use the Euler equation. And using the Euler equation, well, basically the Euler equation says that the derivative of E at U against W is equal to 0 for all W. Another way of saying this is that the representer, the Rees map of DEU, is just equal to 0. We can say this another way as well. We can say that this linear functional is equal to 0 in the space of linear functionals V prime, the dual space. So there's a lot of ways to say this, but this is essentially the Euler equation here. So if we combine the definition of the gradient descent method and we introduce this error and we use the Euler-Lagrange equation, then we can write this recursion relation. So this gives us a relationship between the errors. All right, now another thing I know about the Rees map, remember that the Rees map gives us the object in the Hilbert space, which is the representer of the nonlinear functional, or sorry, the linear functional, right? What do we know about that? Well, we know, for example, if I have the Rees map of DEU, so that's an object in V, right? And we can take its V norm of that. And we said that that's exactly equal to the norm of the linear functional in the dual space norm or the operator norm. Okay, so that's the one we're going to use. What else would we use for the Rees map? We also know that the Rees map for this object here is just going to be equal to the ordinary inner product of the Rees map of DEU against W. Okay, and so that's in V. This is what we call the dual pairing. And this is, of course, an inner product. So when we combine the Rees map and the definitions together, what we're going to do is we're going to take this identity above and we're going to essentially square it. Okay. And what I mean by squaring it is you're going to take on this side, we're going to write the inner product with that guy. And on this side, we'll write this as an inner product with itself. Okay, so that just gives you the norm squared on both sides. And now we're going to FOIL this inner product. And if you FOIL that inner product and use these identities that I talked about up here, you just get this. Now, we haven't used any assumptions about E yet, except for the fact that it has a unique global minimizer. One of the things that we might want to use from E is its strong convexity. Well, we know that strong convexity implies that, for example, the strong convexity of E is going to imply that that dual pairing is greater than 2 mu tau times the V norm of EK squared. So all that we need is this object and that object, well, sorry, this and that object to be the same and this object to be the same. What appears in here is going to be the difference of those two objects then, U minus UK, but U minus UK is just EK. And of course, whenever we have using strong convexity, we get the strong convexity constant mu coming out, and the two tau is just copied over. So this is from strong convexity, all right? But let's work back. What do we have here? All we're using here is the definition of EK. So we can take this guy and replace it with this inequality here. Now what I want to do is I have a minus here, I want to replace this with something larger than that. So I'm going to multiply by a minus sign here, here, and here, and that reverses the direction of this inequality. And that allows me to replace this with something larger, and the something larger gives me ultimately that the norm of ek plus 1 in the um, Hilbert space norm squared is less than 1 minus 2 mu tau. The 2 mu tau is coming from this term, and the 1 is coming from that term. This term is staying as it was, and so that's where we get the tau squared dEu minus dEuk. And this is, of course, the dual space norm or the operator norm squared. Okay, so that's 6. The next thing we want to use is the local Lipschitz continuity, which we have not used yet. All right, so we observe that both U and U naught are in B, and we're going to use this to inductively show that we always have UK belonging to this B. Okay, so what we want to show is that we're always getting closer, and if we show that, then we're always going to be in B. Now, we haven't used yet the local Lipschitz continuity, the local Lipschitz smoothness yet of the derivative. So that allows us to replace this with this calculation here, this being the Lipschitz constant, right? So that's just by the assumption of the Lipschitz smoothness, and it's local only on B. That means that we have to use the Lipschitz constant that is in B. So we're going to replace this with that estimation. And from 6, that allows us to write that the norm of ek plus 1 squared is less than all this stuff times the norm of ek squared. So this doesn't depend on k. That's the nice thing here. It only depends on tau, which we haven't chosen yet, and it depends upon the strong convexity coefficient and the local Lipschitz constant L. Right? So there's our function of tau. Otherwise, it just depends on our choice of tau. And if I change the value of this tau, then that changes the value of this number. Now, the important thing to observe is that, and you can discover this by any means that you like. First of all, this is a parabola, right, that opens upward in tau. So it has this shape. And so basically, I'm going to use just a basic analysis to show that if tau is in this range, then this parabolic shape stays between 0 and 1. Okay, so I'll leave that to you to discover that. Notice that let's see, if tau is equal to 0, what do we have? Tau is equal to 0, then this becomes 1. And okay, so let's see. I thought that that was easy. Let's see if I can convince myself that it's so. So, right, okay. So this function, whenever tau is equal to 0, it's not a very good tau, is here at 1. And so presumably this thing is going to look something like that, right? And come back up here at 1. I think that's what it's going to look like. What happens whenever we put in tau is equal to this value here? So we already know that this is a positive positive parabola. It's opening upward, in other words. And so I believe that if we stick in 2 mu over L squared, you should find that you get exactly 1 again. Or, let's see, is that true? Well, let's see. It's been a number of years since I've thought about this. So let's figure it all out. All right, so if I put that value in, I get 1 minus 2 mu, and then I have 2 mu over L squared, plus if I take tau squared, I get 2 mu over L squared squared times L squared. So I get 1 minus 2 mu over L squared plus, this is what? It is 4 mu squared over L squared, right? So this, I believe we can show is actually not going to exactly equal 1, but it's going to be less than 1. Maybe somebody can plot it out. Actually, I'm not going to do this now because I'll just fumble it up. Maybe I'll put a plot of this thing in there in the notes. So it's probably going to look something. So I think what you can show, maybe it goes down to 1 and then back up something like this. But I'm not exactly sure. So it's something for us to check. I don't want to waste an infinite amount of time on this during lecture. I should have done it beforehand, but I didn't. So I claim, let me just write it like that. I claim that this is true if I restrict tau to be between those two values. And maybe I had some algebra incorrect, but anyway, it's not exactly obvious, but it should be doable. All right, so if that's true, what have we shown? If that's true, then I claim that this number, which we call rho, should be less than 1. And so I get a contraction here. This is, of course, less than EK, which is ultimately, if I assume that EK is in B is less than that, and that shows that EK plus 1 is also in B. So I start off with the assumption UK is in B, and this allows me by induction, if my computations on the previous page were correct, that UK plus 1 is also in B. But the nice thing about this contraction is that it also shows that I have the linear convergence rate that I want, right? Because if this is a constant, which is strictly less than 1, which remains to be shown, of course, but I claim is true, then we not only can show that I have a well-defined method, that means all my iterates stay within B, but I also have a contraction at this rate. Okay, so that's the proof. Now, as I said, you can now kind of optimize this to get the maximum convergence rate possible. Now, this is not necessarily optimal in the sense that it is the fastest convergence rate, but it's optimal in the sense that I can choose tau to make this as small as possible in this regime. Okay, and so if I do that, and by the way, I think I convinced myself that this also has to, yeah, my drawing was not correct. So my polynomial has to be something like that, right? It can't be less than 0. In other words, it has to be greater than 0 and less than 1. But what I want to find is what is the minimum possible value of that? Well, that's found by taking the derivative of this with respect to tau and solving for that value of tau. And if you do that, then you find that value of tau is exactly that, and then the optimal rate becomes that. Okay, so By the way, now you can see clearly that my rate of convergence is exactly going to have in it that non-linear, let's see, let's write it out here. So this constant L over mu that we were talking about before, you can see that it's buried in there. It's the reciprocal of that constant appears in there, squared, of course. But of course, this constant, as I said, is going to appear again and again. This nonlinear condition number. Okay, so that is the the gradient descent method. But here's the problem with this gradient descent method. Like other methods where when the condition number gets large, you get a deterioration of the convergence rate, we see the same thing happening here. Okay? Whenever the condition number deteriorates, that is, it gets closer and closer to infinity, then this constant here is going to approach 1. So we get a deterioration of that. And so for problems where the nonlinear condition number is quite large, this contraction factor might be very close to 1. Okay, so that would be not so great. So that's the big problem with the gradient descent method. There's no way that I can get a contraction factor based on this very simple method that doesn't deteriorate kind of badly as this goes off to infinity. This gets large. All right. So as you see, if that gets large, what's happening to this? This reciprocal is getting small. And so basically 1 minus a small number is very close to 1. Take the square root, it's still close to 1, and that's a problem. So that's something we may have to overcome. So chapter 11 is going to be all about discovering a method which works better than the gradient descent method works and doesn't suffer from this same deterioration as L over mu, this nonlinear condition number, gets large. Okay? So this chapter is titled The Axiomatic Method of Subspace Corrections. So we've seen we've met subspace decompositions before in chapter, I think it was chapter 9. Here we're going to see that in a slightly different context. Okay? And it's going to be used in this optimization setting. So this slide deck is going to have 2 parts. And today I hope to get through 2 sections of this slide deck. I may throw in a 3rd section in this one. It depends on how I'm going to do this. I think there are 5 total sections in chapter 11, so I've got to split this up into 3 sections and 2 sections somehow. In any case, we're going to try to do most of the first 2 sections today if possible. So a lot of this material is based on a paper that I wrote 5 years ago with some collaborators from University of California, Irvine, and from Tufts University. And we were trying to come up with a new strategy for, basically, we were thinking about it as a multigrid method, but at the end of the day, it turned out to just be a new kind of optimization method. So let me give you the description of the problems and the basic axioms that we're going to assume. So the problem is the same as the one in the last chapter. We want to find the unique global minimizer of this nonlinear functional E, this nonlinear energy functional. And as long as we have a lot of nice properties in place, then this energy functional is going to have a unique global minimum, a minimizer, and that is going to satisfy the so-called Euler-Lagrange equation, which we talked about. The Euler-Lagrange problem is to find the same U, it turns out, the same value, the same point in the Hilbert space that satisfies this equation. This is the so-called Euler-Lagrange equation. And so this is basically, the Euler-Lagrange equation is not that interesting, I would say. So basically, there's an optimization problem that you were taught way back in Calc 1, and to find the minimum of this, you just take the derivative and set it equal to 0. Okay, so that's the Euler-Lagrange equation. You're trying to find out what value gives you 0 slope. And that problem is the exact same as the Euler-Lagrange equation. And of course, you needed to determine um, when solving this problem is going to give you a minimizer rather than a maximizer, right? And so we had to differentiate between cases like this, where maybe we were getting a relative maximum or relative minimum, and maybe not necessarily the global one. But whenever we can assume that E is strongly convex and globally Lipschitz smooth, then we know that we're always going to have one single U, which is the global minimizer. And it satisfies both of these equations simultaneously, or both of these problems simultaneously. They're really the same problems. All right, now we do the same thing that we usually do in the multigrid setting. We make some assumptions about our problem, right? And we put together the assumptions in some sort of way to try to say that we have the convergence that we need in certain settings. So again, we'll start by assuming that E is just some nonlinear functional from the Hilbert space V into R. And here are the basic assumptions that we want. So in this case, we're going to assume these all at once, unlike what we did in the multigrid setting, where the linear multigrid setting, I should say, where we might assume this one but not that one, or this one but not that one. So we're going to assume all of these all at once. So this is E0. E0 is the assumption that the energy is Fréchet differentiable. E1 is the assumption that E is strongly convex. And assumption E2 is that the energy is locally Lipschitz smooth. Or said in other words, it's said in another way, we can say that that the first order derivative is locally Lipschitz continuous. Okay, so I think in the previous chapter we called this local Lipschitz smoothness. Now, if it's locally Lipschitz smooth, that means on every bounded set we're going to have a different Lipschitz constant. And so every time we have a bounded set of interest, then we're going to denote that local Lipschitz constant by LB. And that just means the best local Lipschitz constant that we could possibly find on that set. So from this theory, from these assumptions, and from the theory in the last chapter, we can always guarantee that our problem has a unique global solution, a unique minimizer, and that minimizer also solves the Euler-Lagrange equation. Right? That's all basic stuff for us now. So we can use the gradient descent method, but the optimal gradient descent method we said was 1 minus mu over L squared, right? And the problem is, generally speaking, this is going to be big. This could be big. And so we want to avoid cases where that gets big. And the methodology that I'm going to present is going to do that. But the first methodology that we'll present is what we call the successive subspace optimization method, but that has some drawbacks as well. And we're finally going to hit on something in the end that is very useful to us. But the first thing we want to try is this thing called successive subspace optimization. Should be a little bit better than gradient descent, but also have some drawbacks. Now, we need to break our space up into subspaces. And the reason we need to do this is because, well, the method is based on this. the chapter is named after this subspace decomposition type of ideology. And this is going to be useful to us and give us a fast multigrid-like convergence. But what is it? So let's let V be a Hilbert space and suppose that n is greater than or equal to 2. We're going to think about decomposing our space, our parent space, or sometimes this is called the ambient space, into a bunch of subspaces. Okay, so the subspaces, as I said, are numbered between 1 and capital N, where n is greater than or equal to 2. So we're going to assume a couple of, well, first of all, let's say, what do we mean by this notation here? What do we mean by this notation? This means that, remember, if I take two subspaces, I can make a linear combination of elements from those subspaces. If I have three, I can make a linear combination, all possible linear combinations from those different subspaces. So what I'm saying is, if I have n subspaces, I'm going to think about trying to make linear combinations in all the possible ways that I can from these subspaces, and then I'm going to consider what do I get when I make those linear combinations. Well, when I make those linear combinations, I'm assuming that I get back precisely my ambient space V. All right, so that's what this notation means. It means the set of all possible linear combinations, and here I mean n linear combinations of functions from or points from these n subspaces gives me a point which is in V. In fact, it gives me all the points that are in V. So we say that this subspace decomposition is stable, or equivalently that assumption ns1 holds, if and only if there's a constant Ca greater than 0, such that for every V that I start with in the ambient space, there are elements from the subspaces, from these n subspaces, such that I'm going to be able to add those elements up in a linear combination to get V back. Okay, so that's what we mean here. So that's just the linear combination part. The stable part is that when I sum the norms of these guys up, the norms squared, sum I equals 1 to n, Vi in the V norm squared, it's less than or equal to that constant Ca squared times the norm of V squared. Okay, so see, this side doesn't depend on the decomposition that I have, and it's independent of n. This Ca is completely independent of V, so there is a dependence on V of this thing, but it's only in this component here. So it's only depends on V in the way that the norm depends on V, or it only depends on the norm of V, I should say. Otherwise, this constant is just some universal constant for our describing our decomposition. So this is what we call a stable decomposition. If I find this and prove that it's stable, then I can always, first of all, create V through linear combination, and then that linear combination is going to have this property. Now, not all linear combinations will have that property. We're just saying that there, for every V, there is at least one linear combination like that, which is stable. Okay, we don't have to say that all of them are, because you could come up with some pretty exotic decompositions. All I need is that one of them is stable. Now, we say that the energy functional E satisfies the strengthened Cauchy-Schwarz inequality. This one's a weird one, but it's related to the strengthened Cauchy-Schwarz inequality that we had in chapter 9. So E satisfies a strengthened Cauchy-Schwarz inequality with respect to the subspace decomposition. So there's some connection here between the energy and the subspace decomposition. They're not divorced from each other. Or in other words, we say that assumption NS2 holds if and only if E is Frechet differentiable, number 1, and given U0 and V, there is some constant that depends on that U0, which is positive, such that, now this one's a long and complicated one, and so bear with me. It'll be really obvious why we need this whenever we get deep into the heart of the analysis of the successive subspace optimization method. But for now, it's going to look a little bit weird. And all I can say is that it's somehow related to the strength and Cauchy-Schwarz inequality that we met previously in chapter 9. All right, so here it is in all the detail. So there's some constant such that if ui, vi, and wi are all in the subspace vi from I equals 1 to n, and if vi minus 1 and vi minus 1 plus ui are in the sublevel set, the energy sublevel set EU0. So what is this? So remember, we can draw the level curves of our energy function. So the way to think about this is as a topographic map. So you've all seen topographic maps, probably. And let's say we're examining a deep valley. So the deep valley will have its deepest point at this point U, and the level curves will represent the ISO contours or the ISO elevations in the topographical map. Okay, so as I go up and up out of that deep valley, I go to higher and higher ISO elevations, right? So what I mean by this level curve or this sublevel set here is if I pick an initial point U naught, then this guy lies on some level curve. As long as it's not equal to the minimizer, it's going to belong to some level curve. And now this sublevel set that we defined here was the set of all values of U which have an energy, or in this case it would be elevation, less than the elevation of U naught. Okay. Well, in this case, it's the energy map. And so what we're saying is we're looking for all values of U, or let's say V, which have an energy less than U naught. Well, that would be everything inside of here. And so that is precisely this sublevel set. Now, all that we really need to ensure is that all of these guys start and remain in the sublevel curve. And this is what we have to show and will show later on. So all that you need to remember about this now is basically nothing except that everything that we form and throw in the argument of this e function or the derivative of e has to be or has to remain within this sublevel set, some sublevel set, and it's going to be the one that's indicated by this U0. Then if this holds and that this holds, it follows that if the strength and Cauchy-Schwarz inequality holds, that this complicated inequality holds. So as I said, it's not easy for me to motivate what this is or why it's needed. Once we get into the weeds of this analysis here, I'm going to bring this back up and I'm going to say, look at that. That's exact. We need something right here, and it's exactly this, and this is exactly the thing we're going to assume holds. The nice thing is for the energies that we're going to encounter, we can always prove this holds. So that's the important part. Basically, if the energy is sufficiently nice enough, then we can always establish this, and basically that's it. So this is this thing called the strength and Cauchy-Schwarz inequality. Now, as I said, we're always going to need to assume that we're in this, that all of the points that we generate and that we evaluate stay within this sublevel curve or the sublevel set of the energy. Okay, stay in this set here. All right, so that I'm going to prove later on that the algorithm that we use, at least to start with, the successive subspace optimization method, always has this nice property, and that we'll never have to worry that things are going to fall out. All right, now when you look at that that property, describing what we mean by the strength and Cauchy-Schwarz inequality, it has this in there. And this part here is somehow related to the local Lipschitz continuity. In other words, we can bound this above by making the assumption of the or using our local Lipschitz smoothness constant L. So what do I mean by that? Well, if we know that we have this local Lipschitz constant of L in, that's a error there. Um, I think this should say E. Well, I don't remember what it's referring to, but I'll have to fix this typo here. Okay, so but in any case, suppose that you have a locally Lipschitz energy with Lipschitz constant L in B, then we can estimate this piece that appears in here using the local Lipschitz smoothness. And what we get is less than, all this stuff is less than L times the norm of Uj times the norm of Wi. Basically, this here will be the difference of this term and that term. And the difference of those two terms is going to be precisely Uj. Well, if we substitute in this for this term here, we can try to derive a constant and see what constant we get in that case. If we put that in, use this estimate, then we're going to get something like this. But now this is not what we want. This is effectively here a one norm squared, and a one norm squared. And remember, we have this relation for the one norm and the two norm. And what we can show is that the one norm and the two norm can be related, but what's going to pop out is the dimension of V. Right. So what I was arguing was that I can come up with a very crude estimate using the local Lipschitz assumption, local Lipschitz smoothness here. But the nice thing about this assumption is I can often do better, and I can often show that I can do a lot better, in fact, with this strength and Cauchy-Schwarz inequality. In fact, in the next chapter, we're going to prove that we can do a whole lot better than this choice here. The problem is of V can be quite large. If we have some finite element problem where the number of degrees of freedom is in the millions, then of course this is too large. So this way of estimating is way too coarse and too costly. The nice thing is we can often do better using a second derivative and showing that the bilinear form that we get whenever we do the second derivative is often spectrally equivalent to the bilinear form that we are looking for. So what we can do is, if we're careful in our analysis, we can do something a little bit tighter than the local Lipschitz smoothness would give us. So this Cauchy-Schwarz, the strength in Cauchy-Schwarz inequality is actually quite strong and says something useful. Okay. The next topic is the successive subspace optimization methods, which are going to be the first method that we look at, which has a performance that is better, that gives us a contraction rate that is better than the one that we get from the gradient descent method. What is the successive subspace optimization method? So we're going to let our energy satisfy assumptions E1 and E2. No, let's see. It should be E0 and E1. Okay. Do we need to do that's all we need for now. Right. Let's see, do I need to assume anything else? I don't think so. All right. So, well, we can put E2 in there as well if we need it. We just want to guarantee right now that we have a unique solution to our minimization problem. And okay, so The Successive Subspace Optimization method, SSO, is an algorithm, as usual, to generate a sequence of points. And that sequence hopefully converges to, we want to show that it converges to U, our unique global minimizer. It's going to be written in the form of an operator equation. So UK plus 1 is equal to the SSO method applied at UK. And it's recursive, right? So if I get UK, I could get UK plus 1. If I get UK plus 1, I get UK plus 2, etc. They always require the previous iterate. So the question is, how do I compute the next iterate? Given UK, how do I get UK plus 1? That's the big question. That's not too bad. So we're going to start off with, again, U0 being arbitrary. It doesn't need to be all that close to U to get started. And in fact, even to guarantee convergence. So I'm going to focus on computing UK plus 1 from UK. So this is going to be done by a sequence of points which we're going to call VIK. So I'm going to set V0K to just be UK. And now I'm going to generate V1K next, and then V2K up to VNK according to the following rules. I'm going to first create an energy section. So a picture is quite useful in this case, I guess. So we have our U, and we have our level curves. So out here somewhere is maybe UK. So so our subspace decomposition defines what we're going to do for these energy sections. And I'm going to think about them as being one-dimensional, but they don't have to be one-dimensional. But suppose that I'm out here at UK and I think about looking along a certain line of sight in one dimension. And let's choose that in blue. We're going to go along that direction, and we're going to call that direction the direction of VI, or in this case, V1, I guess. So if we're at I equals 1, then we're going to create this energy section, J1K. So how do we do that? Well, we just take the energy and we slice right through it. We make a cut, and that creates a parabolic shape, right? In higher dimensions, this is a little bit harder to visualize, but in one dimension, if I'm taking one-dimensional sections, then it's not a problem. This just gives us a one-dimensional parabola, or a parabola-like curve, right? But we know by our assumptions that we can always sandwich this between what we called quadratic energies, right? The so-called quadratic energy trap. And what we're going to do first is, once we create this section, right? The section is, oh, I should have said here, let's make it general. So this is going to be Vi minus 1K, right? And we're looking along the ith direction, and W is going to represent things along the ith direction. So we're looking along there. We make this energy section, and then we're going to minimize that. We're going to optimize along that direction. If it truly is one-dimensional, then this is what we call a line search. It's just what's called a line search. But in any case, we're going to find the minimum along that direction. Well, if that's a parabolic shape, then we just go to the minimum of that parabolic shape. And that's going to give us something we call the correction, the subspace correction. And you should think about this in the same way you did multigrid, thinking about the coarse grid correction, right? The coarse grid correction is something gotten from the coarse grid. This is gotten from the subspace, whatever we choose, or however we choose that subspace, and it's gotten by minimizing along that direction. Okay? Now, once we get that correction, we're going to apply that to the last update. So basically, if we find out this was our previous point, and our correction is along here somewhere, E, then basically the next point is going to be the corrected value, and that's going to give us VIK. So I'll put VIK there. Once we minimize that, then I get VIK. And I continue on like this. Now, I'm not going to optimize necessarily in the residual direction or any direction in particular. I'm going to always use whatever direction is coming next in my subspace decomposition. The subspace decomposition was set by whatever we chose in that subspace decomposition satisfying our definition. And so, the one big question is what subspace decomposition works best? Well, that's a good question. We don't know yet what subspace decomposition works best or what works at all. We're going to get to that in the next chapter. Well, once we get that, optimize along that direction, add that correction, we get the corrected value. Now when we go back up to the top of the loop and we do that all over again, and how many optimization problems are we going to solve? We're going to solve exactly n optimization problems. Once we get all the way to the end, once we solve for that guy, we correct our last one, I equals n, we get VNK, and that's what we call UK plus 1. Okay, so subspace optimization method is a pretty simple type of method. Now, the thing that makes it not so simple is that these subspaces might not be one-dimensional. They might be high dimensional. Okay, if they're one-dimensional, then it's very, very straightforward. It's just what we call line search, which most of you have heard about. If it's not one-dimensional, then we have to solve a complicated problem, and that's and of course, our solution with that in the multigrid setting is, well, if you have to solve another high dimensional problem, just apply multigrid again. So then you make you make a subspace decomposition of that, and then you solve again, and you just do this in this recursive manner. Now, whenever we are doing this, when we do this optimization here, there's built-in important orthogonality property. And that is because whenever we solve this, the best way to solve this minimization problem is not by doing a minimization, but solving a related Euler-Lagrange equation. Because Euler-Lagrange is easy to understand, makes sense. You just take the derivative along that direction, set it equal to 0, and solve for it. All right, so when I do this step here, okay, when I solve for that guy, I'm really solving a problem which looks like that, involving the energy section. I'm doing a derivative, I'm setting that equal to 0, I'm solving for that correction. But that actually can be rewritten in terms of the energy, because J is written in terms of the energy. When I add the correction on to the previous one, that just gives me VIK. So what we're saying is VIK satisfies this equation here. And this equation here is what we call an orthogonality relation. Now, it's not really orthogonal. It's not, there's no orthogonality here because this is not an inner product. But it is an inner product if we use what's called the Rees map, and we can convert it into an inner product problem eventually. And basically in finite dimensions, this always does look like an orthogonality because we can always transform this into a readily available inner product in finite dimensions. And whenever you have something like this, let's say psi is against W is equal to 0 for all W in V, we call that an orthogonality relation, okay? If psi, for example, if psi is orthogonal to everything in W, and W is a subspace, or in a subspace, then what is that saying? Well, you're getting a picture which looks a bit like this. Okay, so here's my subspace. Here's my point. And things in the subspace are vectors which look like that. This point is orthogonal to that. That means that if I draw a perpendicular, right, or if I think about taking the Well, let's see. What is the, do I have the picture right here? What if how can I be orthogonal to this space um, in all cases? Well, I think what I need is I need my point to actually be here, right? So in Euclidean space, here's my psi. There's my psi, and there's my W, right? W doesn't matter. There's my subspace. Doesn't matter what, you know, where I take this in the subspace. It certainly looks like, in the Euclidean sense, I have an orthogonality relationship, right? So it's clear here that psi is orthogonal to every W in the Euclidean sense. But of course, in hyperdimensions, it's impossible to visualize this or think about what this looks like, and you have to use this simpler mnemonic device, I guess. But this is what's called an orthogonality, or in this case, what we call a fundamental orthogonality relationship. And this method of subspace corrections always has this property built in because we're always doing a correction via a minimization. And as I just argued here, doing that correction via the minimization allows us to write this orthogonality relation. Another way of saying this, by the way, is that this linear functional is exactly equal to the zero linear functional in the space vi prime. Okay? And now notice that this orthogonality relation is with respect to this subspace, vi. So this is always perpendicular to everything in vi. Another way of saying this is, as I said, dei or vi k is the zero in vi prime, the space of linear functionals on vi. Um, Interestingly, and you might remember this from numerical analysis class, whenever I take vi to be one-dimensional spaces, then the computations that are involved in the subspace correction method are exactly like the Gauss-Seidel method. Now, we saw this whenever we were minimizing this functional. So the one that we were optimizing was E equals, say, E of x equals 1/2 x transpose A x minus B transpose x. So, and this A is SPD. So back in numerical analysis, we examined this linear function, this nonlinear functional, this quadratic functional. And what we did was we minimized this over uh, different directions in the space Rn. So for example, we would minimize along E1 first and then minimize along the canonical basis vector E2 and then along the canonical basis vector E3. Well, this precisely gave us the Gauss-Seidel method. I don't know if you remember that, but that's the case. Interestingly, the analog for this is what is called the nonlinear Gauss-Seidel method. And it's called nonlinear Gauss-Seidel whenever this energy is not quadratic. Okay, so we can come up with various hyperdimensional energies which are non-quadratic. And then if I minimize over different directions, one-dimensional directions, successively, this just gives me what's called the nonlinear Gauss-Seidel method. Well, the successive subspace optimization method can just be thought of as Gauss-Seidel, or it's some sort of generalization of Gauss-Seidel method to this nonlinear regime, but also where when I do the when I do this optimization over subspaces, I don't necessarily have to use one-dimensional subspaces. Okay. Gauss-Seidel says you should use one-dimensional subspaces. And so, well, let's see. So what I can do then is I can say, well, if I have some finite dimensional space, let's say something like a mesh, um, well, let's see, will that be easy enough to, let's think about it like this instead. I'll draw that later on and when we come back to it. Let's think about decomposing Rn in various subspaces. How could we do this? Well, so what I'm going to do is I'm going to use the span of E1. That's going to be my first subspace. And the span of E2 as my second subspace. And the span of En as my nth subspace. I guess in this case, I probably should use, to make the notation match, capital N. And so that's all I'm saying. If I have a finite dimensional problem, um, if this is my V, and this is my subspace decomposition, right? So this would be V1. This would be my V2. This would be my Vn. Perfectly good example. And then suppose next that my energy is quadratic like this, where A is SPD, then this is nothing more than Gauss-Seidel. So SSO is Gauss-Seidel. But now suppose I take, if I use subspaces which are not necessarily one-dimensional, but might be spanned by, a collection of other vectors. Okay, maybe I combine these two together and I combine a few of these together into one subspace. Well, that is another generalization of Gauss-Seidel. Then finally, I can say, well, suppose that the energy that I'm dealing with is not necessarily quadratic. Well, that's another generalization. And so that generalization ultimately is exactly the same as SSO, Successive Subspace Optimization technique. Now, the idea of the proofs that we're going to go about in the next lecture, next few lectures, are going to be trying to show that we get an energy contraction of the following form. Basically, what do I know about E at U? Well, if U is the minimizer, then any other value of U, which is not U, is going to give me an energy which is bigger than that of E than at U, right? So this number here always has to be bigger than that number. So their difference has to be greater than zero. Same here. But what I want to do is I want to show that I get a contraction of the energies. If I can show that I get a contraction of the energies with a linear rate of contraction, then I can prove that I have a convergent method. I can prove that I converge in norm in any other sense that I want. Now, the thing that I want to show is that this rho here is not going to deteriorate as the condition number, the nonlinear condition number L over mu deteriorates to infinity. So that's going to be the main technique. I'm going to try to show that I get a energy contraction like this, where rho is some number which is between 0 and 1, strictly less than 1, but does not depend poorly on the nonlinear condition number. All right, so the main little result that I'm going to use to prove that is given by this result here, which we don't have enough time to cover. It's a very simple little calculus result, a little sequence result. And basically, if I assume that I have a sequence of numbers that are, I guess, do I have to assume that they're all positive? I think so. Positive numbers that satisfy this, then I can show that they contract. And I can show that they not only contract, but they converge monotonically to 0, and at this rate. if I can establish that, then the rate of contraction is going to be this. So that's going to be this is going to be a result that we use over and over again. So we're going to put this on a pedestal, I guess. We're going to prove this at the very first next time. But again, I want to remind you that we won't have class on Thursday. Thursday is our honors day. No class on Thursday. So the next time we'll meet is on Tuesday, where we'll pick up with this monotone convergence result. So that's where I'll stop, and I'll take any questions you guys have.